Hi guys. So this video is going to be about nucleophiles and their reactions with aldehydes and ketones. So a nucleophile is a compound where there is excess electrons, and nucleophiles like to bond to compounds that lack electrons. So if you look at these aldehydes and ketones, the carbonyls, these carbons don't have any only have the electrons and the bonds. They don't have any of their own lone pairs, and so they're seeking electrons, and our nucleophiles are going to give them electrons. So the three main compounds you're going to see nucleophiles with are carbon, nitrogen, and oxygen. So in the carbon nucleophiles, it's going to be a I'm sorry. It's going to be a carbon with a lone pair on it, so it has a negative charge connected to sorry about that. It's going to be connected to a more positive element, so like this lithium or the phosphorus here, usually. And so this is actually a special one. We'll save that for a little later. Um, Nitrogens are just basically any nitrogen with two or three hydrogens on it, because nitrogens have their own lone pair naturally. Like when you fill all the um, orbitals, they'll have their own lone pair and have a neutral charge. And then oxygen is going to have two lone pairs when you fill its other orbitals with bonds. And so, yeah, so these lone pairs are what's going to be reacting with the aldehydes and ketones. And obviously, the ketone is a carbon oxygen double bond, where the carbon is bonded to two other carbons, and an aldehyde is a carbon oxygen double bond, where the carbon is bonded to another carbon and a hydrogen. So let's do a reaction with carbon. So we will just say we have this cyanide electrophile here, and it's going to attack acetone, which is the most simple carbonyl, or the most simple ketone. So what's going to happen is, like I said, our nucleophile, so this set of electrons, is going to attack the electrophile, and in doing so, um, it's going to knock these electrons back onto this oxygen of the carbonyl. And so when I picture this reaction, I think of like the carbonyl as like kicking its legs up, and so we're gonna have these two where the legs were kicked up. We're gonna have our oxygen here, which now has an extra set of electrons on it, so it's negatively charged, and then we're gonna have the carbonyl that just came in and bonded to the bottom there. And so when you do these reactions of carbon nucleophiles with um, ketones and aldehydes, you're going to have this extra negative charge from the carbon. And so usually what you're gonna do, or what you're gonna see, is just that this reaction takes place in a acidic solution. So we have our aqueous solution, and it's just gonna get protonated. So it's gonna pick up. Oh wait, let me go back to the red. It's gonna pick up this hydrogen off the acid or the hydronium, and then we're going to have an alcohol. So as you can imagine, if we do the same thing with an aldehyde, we're going to get pretty much the same answer, except the one spot that's different between the aldehydes and ketones is also different in your final product. So I'll just draw. So this is just hydronium because it's acid and water forms hydronium. And so then we're going to get this, where we have the alcohol from the oxygen on the carbonyl, the hydrogen, because it's one of the bonds to this center carbon in aldehydes, and then our nucleophile, which we have to the added to the carbonyl. So then when we do this same reaction with nitrogen, it's quite similar, so I'm just going to draw out the reaction, and you can pause and see if you get the electron movement right, or you can just follow along. So once again, we're going to attack acetone, and our electrons are going to attack here, knocking these electrons back, and it's going to give us a compound where we have a negative oxygen, but this time we also have a positive nitrogen on the opposite side of the product. And so obviously this is an unstable intermediate, but what's going to happen is so it's going to be an aqueous solution again, and I'm actually going to draw out a water here. And what's going to happen is this, so we'll draw hydronium up top too. Oh no, I'm at the top. Ruh-roh. It's an ugly hydronium, but you get the idea. So from the acid, or the hydronium, the oxygen is going to pick up a hydrogen again. So, whoop. And our nitrogen is going to lose a hydrogen to water. So this electron pair is going to bond here, kicking these back, and we will have an alcohol with an H2. So our nitrogen compound has lost a hydrogen, and our carbonyl has gained a hydrogen. So, yeah. And the same thing would go for aldehydes. If we had hydrogen here, we can just keep it here throughout the whole reaction, and that would be our product. Alright, so the last set was the oxygen carbonyls, or I'm sorry, the oxygen nucleophiles bonding with carbonyls. And so most often you're going to see an alcohol. So I'll draw butyl alcohol here, and then I'll draw acetone again because, why not? It's easy and we've been working with it. And so in oxygen nucleophile reactions, the lone pairs on the oxygen are going to attack the carbon of the carbonyl, and once again it's going to boot these electrons off, and we're going to get a negative O, and then it's going to have a positive O at the same time. which is kind of strange, right? At least I think it's just kind of funny, I guess. And then we are going to do the same thing that we did with nitrogen, where we have a acidic reaction. This can or acidic solution, an acidic aqueous solution, and this can also happen in basic solutions. Um, this is the same idea, except that the hydrogen is coming off the water, and the hydrogen from so the hydrogen protonating is coming off the water, and the hydrogen coming off the geez Louise, I'm sorry, is coming off the main molecule onto hydroxide. But anyway, we're doing it with acid, so we're just gonna say this comes here, this comes here, and um, this picks up this hydrogen, which comes here, and this forms a hemiacetal or a hemiacetal. And if we were to do this again with our product, we would actually just replace this H here with another R group. So here, I'll just draw this out down here real quick. So if we react this with another equivalent of our starting reagent, we are going to get an acetyl. So not just a hemiacetal, but an acetyl where the um, alcohol has been replaced by this R group again. So this reaction is one equivalent, and this reaction is another equivalent. So to get from here to here, you need two equivalents. Alright, so the last major reaction is the Wittig reaction. Right? Sounds like with a V, not a W. And in this reaction, we are taking this special carbon nucleophile that I said we'd get back to, and we have a really unique reaction where it forms a ring and then final product, and then we get our final products. So we have our positive phosphorus and our nucleophilic carbon here, and the lone pair from the carbon, like always, is going to attack the carbonyl, booting this back, and so we get this where we have an oxygen bonded to a carbon, and the oxygen has picked up this lone pair from the double bond, and the carbon is bonded to the carbon group on the phosphorus or triphenyl phosphorus. And in this situation, instead of just protonating the oxygen like we have on the other reactions, the oxygen is actually going to bind to this positive phosphorus. And in doing so, we create a an oxyphosphotonic ring, and that's just where we have this 4-point ring where all these are bonded together. And then to finish it off, the ring's actually going to break in a very interesting way, where the carbonyl, what was initially the carbonyl and is now the carbon-oxygen bond, forms the electrons move, forming a double bond between the oxygen and the phosphorus, and the bond between the initial in the initial nucleophile. The electrons move to the carbons to form a carbon-carbon double bond, and we get these really interesting products. So these are ours, and that's just because if we are attacking a any carbonyl, we could have ours on it, right? They could be bigger than just the CH3 that I have shown here. And that's all for that's all for today. That's all for my nucleophile reactions. So thank you. I hope that helped.